Power series representations of functions can be used to help us integrate functions that do not have simple antiderivatives. So we can write the antiderivative of this function as a power series, provided we can actually write out a power series for the function itself. Then we can just integrate the power series term by term to evaluate the integral. So the first step is to be able to write this function arctangent as a power series. Okay, we know how to integrate arctangent, but there's this 1 over x that's here, right? So it's arctan over x. So let's remember that our function arctan of x has a derivative 1 over 1 plus x squared. Okay, and this function can be written or can be regarded as a geometric series, a sum of a geometric series like this, right? Whose radius is negative x squared, the little r I should say, is negative x squared, and constant a naught is just 1. So this as a geometric series is the sum, n goes from 0 to infinity, of 1 times negative 1 to the n times x to the 2n. And so this is equal to the arctangent function. Now, be very careful here. We've studied this power series of this one in a previous example, and we showed that this only converges when x is between negative 1 and 1, right? Strictly between negative 1 and 1. So that's fine, okay? It's fine. But by the way, this means that the radius is 1. And there we go. That's anything we do from here is probably not going to change the radius. So this is almost certainly the answer, but we'll come back to this at the end. What we want to do now is write down a formula for the power series of arctangent. This is the power series for the derivative of arctangent. So what we need to do is integrate out this derivative, right, to get a power series for arctangent itself. And so we can integrate term by term. And what we learn then is the arctangent of x is equal to the some constant, so some constant c, plus the power series, n goes from 0 to infinity, negative 1 to the power n times x to the 2n plus 1, integrate, over the new power, which is 2n plus 1. Okay? And so there we go. There is a power series representation of arctangent. Remember, the unknown constant is not truly unknown, though. What we have to do is plug in some value in this interval that we know the answer to, and we can try to compute this. And the best one is almost always the center point. So the center point here is 0. And we know that arctangent of 0 on one hand is 0. On the other hand, it's c plus the sum, n equals 0 to infinity, negative 1 to the n, 2n plus 1, x to the 0 to the 2n plus 1. And this is just a bunch of zeros, right? It's just a bunch of zeros. And so all we're left with is that c, the unknown constant, is actually a 0 for this function, right? We did an example of a log function previously in these notes, and that one did not have c equal to 0. It had c equal to an actual constant that was not 0. All right, but what we've learned then is that the power series for arctangent centered at 0 is given to us simply by this sum. N goes from 0 to infinity, negative 1 to the power n, 2n plus 1 on the bottom, all times x to the 2n plus 1. And what we want to do is we want to integrate arctangent x over x. So what do you think we do? Well, we go through, we divide by x, right? And this is going to be in an integral, so we're not worried about the fact that x could be 0 here. And what we find is that when we do this, look what happens. We can just combine, right, term by term, combine the powers of x, and we find that every term here starts with at least one x. We can cancel them, right? And so arctan of x over x has power series representation. N goes from 0 to infinity, negative 1 to the n, 2n plus 1, x to the 2n simply, right? We've divided out an x. And if we want to evaluate this integral then, we can just do the integral, at least on the interval of convergence, which is, at least the radius is still 1. So the radius is 1. The interval may or may not include endpoints here because we took an integral, right? We integrated. We're not concerned though. So we're just, at least on this open interval, the integral of arctan x over x dx is equal to the sum of the integrals of the components, right? So negative 1 to the n over 2n plus 1, x to the 2n dx. And when we integrate this, we end up with sum n from 0 to infinity. We end up with a constant, sorry. right? We end up with a constant plus this value, sum n equals 0 to infinity, negative 1 to the n over 2n plus 1 quantity squared, x to the 2n plus 1. All right, and so this is the antiderivative of arctangent of x. If you want to think of this as an antiderivative, then in reality, so even though the radius of convergence of this power series solution is 1, and it makes perfect sense here, the integrand doesn't make sense as 0, right? And so this is defined, and this is equal to the antiderivative of this on the intervals from 0 to 1 and negative 1 to 0, but that's it, okay? Because 0 is not in the interval. So as far as an antiderivative is concerned, you have to delete the point where this is not defined. But otherwise, this is correct, okay?